Hi folks, this is AAT Notes for Section 1-4, Systems of Equation. A system of equation is a set of two or more equations. So if you have two equations, like here's two lines, we've been graphing lines, or it could be more than two lines, or it could be even two equations that aren't lines, that's a system. And to solve a system means to find the values of the variables in the equation that make both of them true. So you're going to find an xy coordinate that makes this one true and an xy coordinate that makes this one true, and it has to be the same xy coordinate. So you need to know these words. There's two different things that can happen when you have a system of equations. Either they're consistent systems, which means it has a solution, or they're inconsistent systems, which has no solution. Consistent means if they have a solution, they're going to intersect in some way. They might intersect at a single point, or they might be the same line and intersect every point. So if they're consistent systems, there's independent and dependent, two possibilities of consistent. Independent means they're two separate lines. And so if they're two separate lines, let me get this out of the way, then they're going to have two different slopes. This slope is 3, this slope is -1. And so these lines are two separate lines. They have one solution, and that solution is that one crossing point. The lines intersect once. Dependent systems are lines that end up being the same line. So when we look at these two lines, 2y plus 4x equals 14 and 3y plus 6x equals 21, you can't necessarily tell, but if we simplify them both, if we divide this one by 2 and we divide this one by 3, we can see they're actually the same line. So they would fall right on top of each other. So they have an infinite amount of intersection points. Intersections are just points they share. Because they're the same line. So same slope, they have the same y-intercept, and the graphs are the same line. There are infinitely many solutions. So the third situation are these consistent systems. These inconsistent systems are never going to cross, which means they're parallel lines. And parallel lines have the same slope, but a different y-intercept. And it's important that they have a different y-intercept because these two have the same slope, but they're also the same line. They have to have the same slope, different y-intercept, so the lines are parallel, which means there's no solution. They never intersect. Okay, so there's three ways, as you know, to solve a system of equations. The first one is graphing. So we're going to graph the two. This is in standard form, so remember the slope in standard form is negative a over b. So if we go to the y-intercept and x-intercept are not very nice here. The y-intercept, remember if we cover up the x, the y-intercept is actually, plugging in 0 for x, -7 over 4. Yuck. The x-intercept, if you cover up y, plug in 0 for y, you're going to get -7 over 3. So both not great points. But let's look at the next one. The slope of this line, opposite A is -2 over B is 1. Slope's -2. The y-intercept here is quite nice, is -3. So 0, -3. So since it's so nice, I'm going to start with this line. Plot the y-intercept first, 0, -3. Rise -2, so that means go down 2, run 1, down 2, run 1, or up 2, back 1. So that's my first line. You should always use a ruler or a straight edge to draw your lines, especially when you're trying to see where the two cross. Now, if you have a fractional exponent, intercept like this, 7/4 and negative 7/3, we can try to graph it, but it'd be much nicer if we could find a nice point that would work really pretty here. Like, for instance, I can just think, what would make, if I do 3 times something and 4 times something, give me a negative 7? I know 3 plus 4 is 7, so if I plug in x is negative 1 and 4 is negative 1, negative 3 plus negative 4 is negative 7. So this is a lot nicer of a point that I could plug in. So if you have an x and y intercept that are fractions, I'd rather you not try to graph those. Try to find another nice point by just plugging in numbers until you get a nice integer point. And sometimes that's easier than others. If you can't, you can always use the fractions, but it's going to be harder. So negative 1, right here is a point on this graph. Then I'm going to do the slope from that point, down 3, run 4. 1, 2, 3, 4. Or up 3, back 4. Okay, so you want to graph it real carefully. And remember, for two systems of equations, we're just trying to find where they're crossing. And the point they're crossing, we can see, make sure you answer the problem. The solution is the point, negative 1, negative 1, where they cross. We can check it by plugging it in. Both equations. We know it works on the first equation. We just did that. It doesn't take any time. It's worth your time. If I plug negative 1, I get negative 2 minus 1 is negative 3, so it checks out in the second one too. So plug it in and check. It's worth your time. Okay, using substitution method to solve a system. Often graphing is not the best method to find the solution, and this is especially true when one solution contains non-integer values. We can also use elimination and substitution. For substitution method, you always want to first, trying to use substitution, get either x or y by itself in one of the equations. So I could do it to either equation I want to. Now when I look, okay, the y is almost by itself here. The x is almost by itself here, so I could choose either equation I wanted to. Let me close that. So I'm going to take this top equation and solve for y. Y plus 2x equals 11. So if I'm getting y alone, y equals negative 2x plus 11. And then once I have y or x alone in one equation, that's equation 1, this is equation 2, I'm going to plug that in for y in the other one, because if y equals this, I can plug it in for y. So now in that equation 2, I have x plus y, and y is negative 2x plus 11 equals 5. Now I have a nice little easy equation to solve. X minus 2x is negative x plus 11. Subtract 11 from both sides. Negative x equals negative 6. Multiply or divide by negative 1. So x equals 6. Now we want a solution. So first we got x alone or y alone in one equation. Then we plug into the other equation for the variable. Then we solved. But lastly, we need an x and a y. Get x and y. Plug back in. So we found the x. we can plug that x back in any of these equations. This one, this one, this one that had an x and y. So if I plug x equals 6 into this equation, I get 6, that's x, plus y equals 5. Subtract 6, and y is -1. Put your answer in an ordered pair. 6, -1 is the solution. Again, I can check it super easy by plugging in 6 and -1 for both equations and making sure it's true. Okay, number 3, for elimination method. For elimination, first thing is to try to put both equations in a nice, pretty standard form. You don't have to do this, but if you consistently do this, it makes it a lot easier. Standard form is to get the x's and the y's on the same side. So these are both have x and y on the same side, but that top one has fractions. I want to get rid of those. So to get rid of the fractions, I'm going to multiply by the common denominator. Well, the common denominator for 3 and 5 is 15. That'll get rid of all the fractions. So if I multiply by 15, 15 over 1 times 2/3, 3 will go into 15 5 times, and 5 times 2 is 10x. Got to multiply it times every term. 15 times -3 is -45y. And 15 times 1 over 5, 5 will go into 15 3 times, so that is 3. So there's one equation. My other equation is 2x minus 9y equals 4. And now to eliminate, we want to try to make one of the x's or the y's go away. So I can see, well, if I make the second equation multiply by -5, that'll make this 2 a -10. If I add it to the +10, it'll subtract away when I combine the equations. So I'm going to rewrite these. Oh, I'm running out of ink. So the top equation is 10x minus 45y equals 3. The bottom equation is -10x. -5 times 9 is plus 45y. -5 times 4 is -20. Okay, I'm noticing something here. These are parallel lines. They have the same slope. I can see -a over b would be 10 over 45 for both. So that kind of gives me a hint of what my answer is going to be. So when I add these two equations together, the 10x's go away. Make sure they're opposite sides. The 45y's go away. So I got 0 on this side is equal to -17. Well, 0 is never equal to -17, so there is no solution, which makes sense for what I was saying earlier. These are parallel lines, same slope. Which means they're inconsistent. No solution. So you can write it as inconsistent or you can write it as no solution. Okay, example 4 here. Let's use any method. So I think on this one, since it's already in standard form, we always want to try to use elimination or substitution because graphing method is just kind of a pain. So I'm going to try to use elimination. Because for substitution, you'd have to solve for x and y, and that doesn't solve very nicely for x and y. So I'm going to multiply the bottom equation by -3. I'm going to choose -3 because that'll make this -9, and my 9's will go away. So rewriting 9x minus 5y equals -4. Write everything out, show your work. -3 times 3x is -9x minus 6y equals -3 times 6 is -18. Okay, so take a second. Let's pause right here and see if you can finish this problem. Pause. Here's my pause button. Okay, if I solve this, the 9x's go away. I get negative 11y equals negative 20. Wait a minute, did I do that? Negative 18. That was a negative 4. Sorry, I wrote that wrong. So that's negative 22. Negative 4, negative 18. So I'm going to divide by negative 11. And y is equal to 2. Remember, I want an ordered pair, so I need an x. So I can plug that y into any of these equations. So if I plug it into this 3x plus 2, y was 2, so plug it in. 3x plus 4 equals 6. Subtract 4. 3x equals 2, so x is 2/3. So our answer is 2/3 2. So this would be consistent because it has a solution, and independent because they're two independent lines. Independent. There we go. This one up here was also one solution, so it's consistent independent as well. All right, go try some on your own.